Okay, we have done manually both the problems, that is flow through a rectangular duct and also flow through a triangular duct. Because we are doing manually, we had to restrict ourselves to a small number of cells, but you could write a computer program and then increase the number of cells so that you would actually get a proper solution, and that is what is done by a student in a regular CFD course here at IIT Madras, and the results are shown here. What we are seeing here are the velocity contours for the rectangular flow case with 5 by 5 cells, 5 in the x direction, 5 in the y direction, 6 in the x direction, 6 in the y direction, 10 in the 10 by 10 here, 15 by 15, and 60 cells in the x direction, 60 cells in the y direction, all done using the same program. So you need to be systematic in understanding how to do it and how to code it, but it's not difficult to write the computer program, and if you can write that, then you can easily do these kind of things. You can run it for any number of divisions and then you can get a solution. And what we see here is that as we increase the number of cells here, that is number of grid points, then the contour lines become very smooth. In all cases you see that the maximum velocity is at the center. The velocity value here is given in terms of color coding with the different color contour values are given here, and the contours obtained with 60 by 60 divisions here is shown here, and you can see that it's very reasonably looking velocity profile is what velocity contours are what we see. In the center we have the highest velocity, and then as we go towards the edges, then we have lower and lower velocity, and this is what we precisely expect. But in order to get this kind of smooth variation, we had to have large number of cells here. So this is one of the features of CFD, that is you need to have a large number of cells in order to get a good solution, and so it's not fit for hand calculations. Only if you can do computer based calculations you can do CFD. Another way of looking at the results is shown in this table here, and here we are looking at the total discharge, that is the volumetric flow rate through this duct cross section. That is, you get the cell values at this 25 points here, and then you just add them up, or you can do a weighted average based on the area of each tile, and then you can get a total flow rate here. The numbers do not matter, it depends on what size they have taken and what pressure gradient they have taken, but in all these cases the pressure gradient, the constant C, is kept the same value, and the dimensions of the duct are also same, the fluid is also the same. What is being changed is the number of points here, and we see that as you increase the number of points, this value which is 18, 19.3 increasing, but as you increase further it is becoming constant. So here there is 21.9, 21.93, 21.94. So it's in a way it's becoming a constant value. So there won't be significant difference between success values as you increase the number of grid points, and that is when you can claim that you have a grid independent solution, and we expect the grid independent solution to match with the correct solution, exact solution of the equation. In cases like this where there are modeling errors are very small and the approximations that were made in doing the discretized equations, we said that we will give values at only grid points. Okay, when we compute the flow rate through this, we multiply the grid point velocity times the grid area, the cell area. So there is an approximation there. So it is not a numerical, it is not an analytical integration, it is the approximation that is introduced. But as you increase the number of tiles, as you increase the number of grid points, then that error becomes less and less, and we see that happening here. The same thing can also be done for the triangular duct, and here again we have with 100 cells, 400 cells, 2500 cells. and what we did in hand calculation was just 9 cells. Okay. Again, you have to do coding and you have to do you have to be good at it in order to get it going, but it's possible, it's been done by students like you, and if you do that you can see again as you increase the number of grid points you get smooth contour lines. Again you have at the center you have the highest velocity, and as you go towards the corner the velocity decreases, and nice and smooth kind of things we are getting here. There are some small variations here. Those are the kind of errors that may be expected. If you increase the number of grid points, if you increase the accuracy of the calculation, even those may disappear. And again, the total discharge that is calculated through this cross section for the same C value and for the same cell dimensions in all cases, the same duct dimensions, but just by increasing the number of cells you can see that it has gone from 182 to 175, 174, 173, 173.7, 173.55, 173.45. It is converging to a value, and that again is a characteristic feature of CFD. Okay. So, with these two examples and using two different approaches, which is the finite difference approximation and the finite volume approximations, we have seen how we can take a partial differential equation and then convert it into algebraic equations and then solve them using a certain methods. Any methods, we have used a certain method. We can get a solution which results in contours like this, velocity contours like this. So, this is essentially what CFD is, but this is not only aspect of CFD, because what we have done is take the simplest possible case. In actual case we have lot more difficulties that we encounter. The equations that we have taken are only a Laplace type of Poisson type of equation. So, in that sense it is probably the simplest form of the governing equations that we can find in fluid flow. The actual governing equations are much more complicated, and it is not, we have solved only one partial differential equation. In actual case you will have maybe 2, 3, 4, 5, 8, 10, whatever number of equations that may be there, even hundreds if you do chemical reactions, and then if you have a large number of species then you have hundreds of reactions are also possible, hundreds of equations are possible. And so, when you are dealing with those many number of equations, and when you are dealing with the nature of the equation which is different from the simple case that we have taken here, it is a boundary value problem and it is a relatively easy problem. So, for all those things you have a lot more complexity that arises in the actual CFD solution, and that is what we are going to do in the rest of the modules. In the next module, this is the first module in which we have looked at essentially the skeletal structure of a CFD approach, and done for two different cases using two different approaches, but both are essentially following the same route of converting a partial differential equation into a set of algebraic equations and using a special method to solve those algebraic equations and getting the final solution. So, the same kind of approach will be discussed in much more thoroughly, and we bring in a whole set of new concepts which are needed to get a solution, a satisfactory solution for the real case. We can see that simplistic approaches that we have used here cannot be universally applied. Okay. So, in the next module we will try to look at what are the equations that would actually appear that we need to solve when we are dealing with the general case of fluid flow involving for example flow, heat transfer and chemical reactions. Okay. So, these equations, we will try to establish these equations from fundamentals so that you have a good understanding of this, and we should keep in mind that the accuracy of the CFD solution is only as good as the accuracy of the equations that we need to solve. And so, we need to know what kind of equations we are solving and why we are solving these equations. Along with these equations, we also need to have boundary conditions and initial conditions, because we have partial differential equations. So what type of boundary conditions are appropriate and how to specify these is also something that we will see in the next module. So by the end of the next module we will have a good understanding of what equations we would like to solve, and we already have a fairly comprehensive idea of the CFD approach in terms of discretization and all that, but we would like to put that on a more firm footing, and then we look at what is meant by these finite difference approximations and what kind of approximations are possible, and what kind of approximations are good. So these are the concepts of specific to the solution of fluid flow equations, which are needed to be understood in order to get to a proper discretization scheme for a given equation. So we will, in the first part of the third module, we will look at the basics of finite difference methods, and then we look at certain concepts like consistency, stability and convergence, which will dictate the goodness of the solution that may be expected. And in the second part of the module we look at certain tests that can be done to verify the consistency and stability and all that, and we will finally come up with a good way of a template for the solution of a typical partial differential equation that we encounter in fluid flow. So that would be the end of the third module. But as we mentioned earlier, fluid flow equation is not about solving one equation, it is solving a set of equations, and these are coupled equations. So we need to have specialized methods for the solution of these coupled equations. So in the fourth module we look at the specialized methods that have been developed based on this fundamental understanding of the fundamental concepts of the CFD. We look at one or two special methods that have been developed for compressible flow cases, where the equations have a certain character, and what kind of other special schemes that are needed for incompressible flow, which very often occurs in practical applications, but unfortunately we will not be able to apply the compressible flow type approaches for incompressible flow prima facie, okay, in a naive way. So we look at some special methods that have been developed for incompressible flows. So at the end of this module, the fourth module, we will have known what equations to solve and what is the best way of discretizing these things, and then what is the best way of coupling all these things together so that we can hope to get the solution of the entire set of equations. But we have seen today that knowing is one thing, but in order to get a good solution we need to have large number of grid cells, and so that means that you should be solving these equations with a huge number of grid points. Sometimes it can be 10,000, a million is also not unheard of. When you are looking at a million grid points, then your coefficient matrix will be million by million. So you need to have a very efficient method for the solution of these equations, linear equations. If you look at conventional methods, they will not be really good, they will take so much time that you cannot hope to get a solution in your realistic lifetimes of your assignments, or even of your industrial problems, even of your career and all that. So we need to have specialized methods, and in the fifth module we look at the specialized methods that have really brought a CFD solution within the reach of an engineer who can pose the problem on the evening and hope to get a solution with a million grid points the next day morning. So an overnight solution is made possible only with the development of the specialized methods for the solution of the linear equations, for the solution of AW equal to B when A is very large, okay, which has large number of grid points. So that will complete for us the entire spectrum of the CFD things at a basic level. So we know what equations to solve, we know how to discretize them, and we know how to couple them, and we would have efficient methods for the solution of these algebraic equations, so that we can get a solution like what we see for the triangular duct here in a more complicated way. Okay. But this method what we are going to develop in the next 4 modules is based on essentially the Cartesian coordinate system for the simple case like the first case of rectangular duct. When we want to tackle more difficult geometries, irregular geometries which cannot be fitted into a simple Cartesian system or into a cylindrical system or spherical system like the triangle that we have seen, then it is important to it is usually necessary to go for the finite volume method, and then we will in the last module, in the first part of the last module, we will look at a systematic introduction to finite volume method. What we have done is in an ad hoc way. For this specific case of equilateral triangle we have done it. We look at a more general way of doing it in the finite volume method, and in the second half of the last module we will also look at the how to treat turbulent flows, because what we have done is for laminar flows, and turbulent flows are a different beast altogether in terms of the complexity of the physical phenomena, and you have a fairly comprehensive treatment, approximate treatment that is possible for turbulent flows, and that is what we will be discussing in the last part of the last module. So with that we will have a more or less basic understanding of how to do CFD for essentially single component flows, single phase flows. So that is the outline of the whole course, and from next week onwards we will move into the second module.